And after the introduction, you will tell about how you used the new aligned methods to look at the sustainability of the bloom process. We would have had Matthias Gustafsson of Aalborg, but he is sadly sick. But Marie Jones has said, well, I can do his part as well. So that's very nice that it can be possible. And after that, we will hope to have some time for an interactive discussion where we can discuss with you about the methods that we have developed in Aligned and about environmental sustainability in the pulp and paper sector in general. And we'll see how that goes. It depends a little bit on you. And we like to be flexible and we like to learn also from you. And we hope that you think that's interesting. Yeah, person-wise, we have also Rachel van der Sluis, who helps with the organization. Thank you in advance for the, without any doubt, seamless organization.
Good. Yes, and then I will give the floor to you, so you can share the screen.
Thank you. Thank you. Yes, my name is Patrick Reumerman from BDG Biomass Technology Group, and I will tell you something about the general project and the aligned and the case study in aligned for pulp and paper, which is being discussed here. Yeah. First, I work for BDG. BDG is a SME which works on energy and materials from biomass. We are a company that combines RTD with project development and consultancy. And we think this is a good combination because the researchers know what happens in the market, and we as market people know what happens in the new development of new technologies. And we have an extensive track record of more than 25 years with lots of projects and lots of plants and spin-off companies. In our work field, we span the entire chain from the pre-feasibility up to the implementation of the projects. We also look at the entire value chain from biomass to energy materials. So from the availability, resource availability, the logistics, the pre-treatment, the conversion, the various conversion technologies, and to the production of the products and the sale of them in the market. Besides the primary processes, we know also a lot about gamma aspects, and those are related expertise fields such as sustainability, value chain evaluations, financial analysis, legal aspects, knowledge transfer, all things related to the value chains from biomass to energy and materials. We love to work with European partners. We have experience with the forming of consortia, and we love to cooperate in larger and in smaller European projects. And we're always very interested in anyone with new ideas on this part. Then about the Aligned project and the history of the project. That was actually because we worked on an assignment from the European Union where we looked at the opportunities that there are for biorefineries in the EU. And one of the things that we looked at were the barriers for deployment of more biorefineries. And it turned out that the evidence to be gathered for proving environmental sustainability is a barrier because it is costly. LCAs are needed at the product level, so for each product. LCAs, they are open to interpretation. There is no level playing field with the fossil competition because they don't have the strict environmental demands. There are many labels and certifications, but they're not always effective. There are sector-specific methods, like Higgs, MSI in the textiles, and FSC and PEFC in the forestry sector. Terminology is confusing in some cases. And we thought, well, we want to improve that. We want to make that better. And we teamed up with other partners, such as the University of Aalborg, and of course also with Bloom in Switzerland. And we tried to seek to improve the environmental sustainability via improving methodologies and directly via looking at the sector and how they can become more environmentally sustainable. So this is what we want to do. As aligned, we want to advance the scientific field of life cycle assessment and collaborate with industries from these 5 industrial bio-based sectors. The construction sector, bio-based construction sector, woodworking, pulp and paper, textiles, and biochemicals. Those are all industrial bio-based sectors which have quite a reasonable size and thus a reasonable impact. And it's good if the environmental sustainability is improved in those sectors. And life cycle assessment, I don't think I have to explain that to you. It's a decision-making tool to measure the environmental impact of materials, products, services. What do we want to do in Aligned? We want to improve, harmonize, and align LCA methodology for the assessment of these bio-based industries, demonstrate the power of our methodologies to improve this environmental performance, and the third thing, what we're doing here at this moment, to inform, involve, empower relevant stakeholders so that the methodologies are suited for application and that their uptake is facilitated. So that's point 3 is of course essential, an essential element in the whole process. We do that with a very nice consortium of a number of partners. Universities are in there. Aalborg University is the coordinator. I already mentioned that. But we also have Antwerp, INSA, and NTNU. The latest one is the Norwegian University. We have for each of the 5 sectors a case study company. And Bloom is, of course, for the pulp and paper, the case study company. We have 2 research SMEs, BTG and Sustainable Innovations, and 1 sector organization at Centexpel. And from the logo, you can see it's from the textile sector. So, about what we developed. We are already working for, I think, 2.5 years. So we did something in that time. And we have developed a very nice collection of methods. It is based on the best available scientific methodologies. And it is, we've made case studies so that we can try how it works in the real world. So this is what we want to connect the theory and the scientific methodology and the practical real world examples. And it is openly available. Later on, I will make some advertising about how you can access these methods and how you can use them and how you can give feedback back. But that's the essence, it's openly available. So where did we work on? If we take the isophases as a way to structure this, we do LCA. We have worked on a method for generating dynamic background data for prospective LCA. And prospective LCA, for those that don't know it, that is a method to look at future developments on, for example, energy. And if you have a new technology or a technology with a long use phase, then you can make prediction on what the environmental impact will be in the future. So that's prospective LCA. We have a method for identification of market constraints. That is because we think that consequential LCA is in some cases, a better method than attributional LCA. I think Marie will explain more about this, but we have a method for time and space dependent of carbon accounting, because you can do that in a simple way, or you can do that in a way which we hope and think more accurately reflects reality. We have looked at methods for dynamic assessment of climate change, which looks at the accumulation of CO2 in the atmosphere and the release based on the impacts of the inputs of the projects. We have looked at methods for uncertainty and sensitivity analysis. We did not really do very new things, but we looked at what is a good method to describe this in a right way. And we looked at socioeconomic assessment in the bio-based sectors. These methods are all openly available, as what I said. It can be connected, can be found at Zenodo. And there is a link which is here, and the slides will, of course, be available to everybody. And there you can find a description of the scientific methods and tools and guidances to use them, and because we want these methods to be used, and we would like to spread these out. You're welcome to try them, and we would like to hear from you afterwards. So if you can provide feedback on your user experience, especially the things which are not yet clear and great, then please do that. And we do that, of course, also internally, but we really like to invite you to try that yourself, so that we can improve the methods and that they can be more usable. We have tested some of these new methods in the case study of Bloom. The case study of Bloom focuses on the extraction, depolymerization, valorization of lignin. They're a very nice company which has a pilot plant in Switzerland, which uses a method to provide functionalized lignin with various properties which can be used better than the normal crude lignin, which is developed as byproduct of the pulp and paper industry. It's a novel technology, so it will be scaled up in the future. So prospective LCA is, of course, a very good instrument to be used here. It was used, the aligned project, to create decision support for the technology development, and I think this is one of the ways, a very good ways, to use the LCA methodology for this. We will hear more about it from Mary, of course. Well, on this meeting, we would like to consult with you on what you think about what we did. 2 years ago, we did check what Aligned could do and how it could benefit the sector. And now we are 2 years later, we are there to present the results of what we've done and to gather input for what should happen to improve the methodologies, to improve the whole field of environmental sustainability in pulp and paper. I hope that you enjoy this work, and you can still get connected with the Aligned project via the various ways, the website, we do Twitter, okay, the LinkedIn, especially, I think. And we have, of course, a stakeholder network where you can sign up and then you don't miss anything from the project. So that's it for me. Thank you very much. And I think we can now go directly through with Mary Jones about the case study.
All right. Hello, everyone. Let me share. Right. Do you see it in big?
Yes. Yes.
Yeah, we see it now big.
Right. Hello, everyone. Thank you very much for joining this workshop. So I'm Marie Jones. I'm a PhD at EPFL in Switzerland, and my project is co-founded by Bloom Biorenewables. Thank you, Patrick, for the nice introduction. And I was meant to be joined by Matthias, who is a researcher in Aalborg University, but unfortunately, he told me this morning that he was too sick to present. So I'll try my best to present his part of the project. Hopefully that should be okay, but for questions, I might have a bit more trouble, but I'll give you his contact details if you have more questions really on what he did. But, oops. So what we are trying to do at Bloom is getting out more of biomass than we do with conventional processes. So I guess you are already quite familiar with the structure of lignocellulosic biomass. So it's made of two main sugar polymers, cellulose and hemicellulose. And then we have lignin, which is this complex aromatic polymer, which structure is still really much under study. And the conventional processes, they've really focused on the cellulose fraction, so this blue fraction, because that's what's been used to produce biofuels and by the pulp and paper industry as well. And those processes, they leave behind a condensed lignin, so the aromatic groups, they come together and they form those carbon-carbon double bonds that with current catalysis, we don't know how to break. And so we don't know how to valorize the lignin from a materials point of view. And so it's usually just used for energy recovery. And so to improve this atom economy, biomass-tailored processes have been developed in the last decade. And one such process is the aldehyde-assisted fractionation, which was invented at EPFL in Switzerland by my professor and now being scaled up by Bloom. So in this process, we are able to recover the isolated cellulose that can enter the same transformations as the ones from conventional pretreatment processes. We obtain functionalized xylose. So those are new molecules with interesting properties. And finally, we have a stabilized lignin polymer. So instead of having this condensation reaction, we use these protection groups here in red, to prevent the agglomeration. And so with catalyst and high pressure and hydrogen, we can break this complex polymer apart into its constituting monomers. And this is the largest source of renewable aromatics on the planet. So this is really what Bloom is trying to commercialize. So a little bit more about Bloom. As we said, it's a Swiss startup and proud to be. It all started with research being conducted at the Laboratory of Sustainable and Catalytic Processes at EPFL under the supervision of Professor Jeremy Lutterbacke, who developed the aldehyde-assisted fractionation, and it's been featured in a number of highly respected journals. Here, there was a project that I collaborated on to make plastics out of this technology. And so what Bloom is doing is taking this lab scale discovery into a commercial innovation. And this pretty much when I arrived, it was moving from the lab to the pilot scale. And this is a picture of one of my former colleagues that was emptying the reactor in the pilot plant facility in Switzerland. And so from the successful pilot scale trials, now there's the effort is really to move on into the design of a first of a kind process. And to do that, I've been using process modeling tools, and we've been collaborated with companies that also provided this nice 3D image of how the factory could look like once built. But my role in the company and as a PhD student has really been into this process modeling aspect, so taking experimental data and translating them into what it could look like in a factory. So I'm now going to dive a bit more into what this biorefinery process looks like. That's quite complicated, but I'll walk you through each of the steps. So we start with a pretreatment where the dried biomass is mixed with an aldehyde, here glyoxylic acid, which enables the protection of the lignin and the xylose fraction. We add an acid and methyl THF as a solvent. Then after 3 hours of reaction, the mixture is neutralized, and then we filter off the solid fraction. So that's mostly the cellulose, and it is washed in 2 steps, first with the solvent and then with the water. Then we obtain this isolated cellulose. Going back to the liquid fraction of the filtration, we mix it with the washing of the cellulose, and then we have a distillation to enable an efficient recovery of the solvent because it's quite expensive. And so we are left with a pretty viscous paste to which we add water to precipitate the lignin, and then this lignin is filtered. With the liquid fraction, we want first to evaporate this water and then add more acid to be able to fully protect the xylose with the glyoxylic acid. We then add methanol to esterify the molecule because that enables an easier separation via distillation. And then we have a few steps of purification and final crystallization. And this part of the process also enables us to recycle the unreacted glyoxylic acid back to the pretreatment to really improve the material efficiency and reduce the raw materials need of the process. And so what happens with the lignin fraction after this filtration is that it's depolymerized with hydrogen in ethanol in a pressure reactor. And we recover the solvent. And then the flash, in a flash, we vaporize everything except the oligomers. So that's a few of the monomers that are still together, but much shorter chains than the original polymer. And then we designed a 3-step downstream scheme where we are able to recover the main 2 monomers, propyl guaiacol and propyl serengol, as isolated fractions. So with this process, we have a quite big product portfolio. Here I'm going to present some of the applications, but if you're interested in finding out more, you can scan this QR code and that brings you to the website of Bloom. So here, firstly, the isolated cellulose, it's this white fibrous powder, and it can, like the applications that have really been studied by the startup to make this microfibrillated cellulose, but it can also enter any fermentation-based processes that would lead to chemicals and biofuels. Then we have the bioplastic monomer, which is also a white powder after crystallization. And the same molecule has been found to be a good alternative to terephthalic acid to make PET substitutes. It also can be used to make nylons, and there they would replace adipic acid most likely. And then finally, we have the stabilized lignin polymer. So here I'm showing a brown powder, but if you are following Bloom on social media, they announced quite recently that they were able to fully make this lignin white. So that would even widen the scope of application, especially to cosmetics, because lignin has interesting properties in terms of UV blocking and antioxidant activity. Can also be used in anything that has to do with adhesive. It's a good glue. But it can also be depolymerized into monomers and oligomers. And the oligomers found application as fuels, as polyurethane foam that can be used in house insulation. And the lignin monomers, most of the applications right now that are pretty niche and high value markets for pharmaceuticals, but also flavors and fragrances. So with this wide portfolio, we were interested as a company to perform a life cycle assessment, but we had identified the key challenges from trying to do it ourselves. And the main one being this multi-product biorefinery. So it's really hard to know what to use as a functional unit because we produce the 3 fractions no matter what. And so there's not really a driver of which one is the main product and the others are happening. So it was also really hard in terms of how to allocate the burden across those different products. And we were hoping to get from this the participation in this aligned project, some guides in terms of business development to target the solutions that would have the greater sustainability potential. Another challenge is how do we account for the biogenic carbon that comes with the biomass, because we want to avoid an unfair comparison with petrochemicals, which would not, like, sustainability is one of the unique selling points of the company, and so we need to make sure that this is done correctly, but also not hindering the process. And finally, as Patrick said, we are still pretty low TRL, and so this prospective approach was very relevant because we don't expect the technology to be at large scale in the next 5 years. And so for us, it would be very interesting to be able to anticipate any future competition for resources, as well as leveraging other decarbonization efforts that are done in other sectors, such as the energy sector. So then this is when Matthias should have taken over, but I'll try my best. So what did we apply as part of the Align framework that Patrick presented? So we did this cradle to grave consequential LCA. So what is quite special compared to what we had done at Bloom before, especially to extend to the end of life. We usually had only focused on the cradle to gate, but that completely overlooked one part of the life cycle. And also, I had always used the attributional method. And what's very interesting with this consequential approach is that the resources are constrained. So in one of the initial models that we had made, I was using sugarcane bagasse as the feedstock of the process. And that's a residue from sugarcane production. And in my attributional results, it looked pretty good. It's a waste, so it has very little impact. It's biogenic, so on. The results will look really good. And then Matthias ran the same the simulation with the same inventory using the consequential approach, and then the global warming potential just skyrocketed. And what we understood with this new approach is that sugarcane bagasse, if it is used to make chemicals like in the Bloom process, that means that it's not being used to recover energy to fuel the biorefinery. And so you need to import additional natural gas and burn it to cover those energy needs. And we all know that natural gas has a very high impact. So really, with this consequential approach, we are able to see this constraint aspect and this competition, that if we change this in the current market organization, we have the whole side effects that appear, which we would not see with attributional. Then in terms of the biogenic carbon accounting, the aligned framework recommends this -1 + 1. So we give credits at during growth, and then at the end of life, this biogenic carbon is re-emitted, but it allows us to really follow the carbon flows over the entire lifetime and identify key hotspots. To deal with this multi-product aspect, the framework recommends to use this substitution, so trying to map all of the products with alternatives that currently exist, and then say that because we produce 1 kilogram of this, we avoided the production of 1 kilogram of the petrol-based alternative. And finally, for this prospective approach, we used some of the well-established softwares that enable the modification of the background data to account for the future decarbonized energy sector. So now let me go through some of the key results of our analysis. So the first one that I want to present is the global warming potential for 1 kilogram of cellulose pulp, because this is really the product that would resemble the most what the current pulp and paper industry does. And so for the full life cycle from cradle to grave, we have a global warming potential of 2.14 kilogram of CO2 per kilogram of cellulose pulp. And this is how the breakdown looks like. So it's really the end of life, so the burning aspect the re-emission of the CO2 that contributes the most, as expected, but also this DMGX production section. And this will look into it a bit more detail. But I want to point towards the choices that we made for the substitution, that the DMGX would replace terephthalic acid, and that the lignin fraction would replace phenols. So here they come in negative because we are substituting them. So looking into a bit more details of this breakdown of impact, again, we see the carbon dioxide itself by the re-emission through the burning of waste and the end of life. But here we have this glyoxylic acid that is here modeled, produced from fossil resources. And as part of my PhD, not as part of the Aligned, but I've studied how we could produce it differently. And there's an interesting method actually being scaled up in other EU project in the Netherlands using CO2 capture and electrochemical processes to produce this glyoxylic acid. And I'm really able to see almost like now the emissions really drop. So this with further decarbonization of the whole value chain is expected to also be cut down. But what I want to draw your attention to is those steam imports, because by valorizing the lignin for its material application, we're not burning it anymore. And so compared to traditional biorefineries that would be self-sufficient in energy thanks to the burning of the lignin, here we have to import steam generated from natural gas burning. And so that leads to a major impact of the biorefinery. And that's when the prospective aspect can be interesting at looking at other ways of generating this heat, supplying it to the biorefinery instead of natural gas burning, which we should phase out. So next, what Matthias did. So here, that's where I would be have the most trouble in really answering detailed questions. But what was very interesting to look at is that the process really depends on this biomass. And here, if you follow this decision workflow on how this should be modeled, it is the determining product of the forestry industry. And so there is this question of, can this production be increased? And so Matthias looked at both in the case when it can't be. And so he modeled the biomass availability as a marginal mix. So how much more can we take from what is currently produced or used in other applications? So looking at, again, the side effects that if I pull more here, am I not pulling elsewhere? And so this means that, yeah, this is because biomass is the main product of the forestry. So will it be able to increase the production to meet other needs? And so to do this, they made projections, and this is actually in collaboration with what Aalborg did with the INSA partner, where they modeled biomass based on different geographic, botanical, I don't really know how to say that, geochemistry results. So this means to improve the modeling of the biomass feedstock compared to the existing life cycle inventory from EcoInvent. And this is the results when we use this new modeling approach. So we see that the impact would decrease by a bit compared to the original data from EcoInvent. But here, that's where my knowledge stops, is that there was many choices that went into the design of this marginal mix, and that means that there's a lot of variability in how this is modeled. And so it doesn't really mean do we have higher or lower results. It's really more increasing the modeling accuracy by taking this approach. So moving on from the biomass modeling aspect, we looked at the influence of product substitution. So as I presented from the portfolio of products, Bloom produces a wide range of chemicals with many different applications. And so since we are doing this substitution, we map them to what seemed the most reasonable for us as a substitution. But because we have other alternatives, we looked at this sensitivity. So here, the first three bar plots, it's when we assume that the bioplastic would replace a terephthalic acid in PET formulations. And the lignin would be used for phenols. Here, the monomers would be for phenols, and the oligomers would replace short-chain polyols for polyurethane foam production, or here they would replace bisphenol A in thermal paper applications, for example. And we can see that here where we are varying the use of the lignin fraction, the impact doesn't vary so much. So they all seem to be pretty equivalent depending on what we choose. So it's more going to be driven by an economic, yes, more an economic driver than a sustainability driver. What markets should we target first? But when we look at the comparison between terephthalic acid and adipic acid to make nylons instead of polyesters, we then see a huge decrease in the environmental footprint if we were to target adipic acid substitution rather than terephthalic acid. So this is really something that is guiding the business decision of how do we market our products, and therefore LCA identify that this would promising, whereas the market price of terephthalic acid and adipic acid are pretty equivalent. So it would really be a sustainability driver. Next, we looked at a glimpse into the future using this prospective assessment method that Patrick had mentioned. To do so, we used the premise tool, which is also accessible with the files on the Zenodo repository, where we modified the background data of the EcoInvent inventories using some of the scenarios that are developed in this integrated assessment models. And they are the ones that are used in the IPCC reports to talk about more future, like those narratives for the future of Earth. And so here, this premise is very interesting, but it is limited to only changes in the power generation and the fuel sector, as well as transportation, but it doesn't change any of the chemical sector, or it doesn't change any of the pulp and paper production. So those background data are not modified. Yet it's very interesting, given that the biorefinery is dependent on steam imports. This would be modified in the background depending on the energy mix. So this is for scenario SSP2, which follows the current trend. So it's the business as usual, but we have some, no, sorry, it's the intermediate case. It's not the business as usual. Business as usual is the one below, where we keep really being dependent on core resources for a long time beyond 2050. So that's the business as usual scenario, and the SSP2 scenario is where we follow the current trends towards decarbonization, but we make slow progress. And then SSP1 is really we have a disruptive change in the way we live to go towards more sustainability. And so when we modify this background data, this is how the global warming potential for the cellulose pulp looks like. So we really see if we go in a decarbonized world, then it would really drop significantly, and that's mostly due to the move away from natural gas burning for steam generation. And for the other scenarios, there would still be a decrease in the impact, but not as insignificant as with the future decarbonized. So from those specific results to our case study, we tried to generate some more generalizable insights that could be wider applied to the whole sector. And the first one that we came up with was that by having a material valorization of the lignin, it modifies the energy balance of the biorefinery, which moves from a net producer of energy, sometimes biorefinery can even export the electricity, to a net consumer, having to import steams from natural gas burning. So it really, this use of the lignin really improves the carbon efficiency in terms of biogenic biomass utilization efficiency, but it creates this dependency on energy imports that is really visible from LCA results. And the second insight that we came up with is that with this consequential LCA approach, we are able to look at the resource availability and at those trade-offs between like if we can get more of a certain resource. And so it accounts for those broader market dynamics, which can then be very useful in terms of anticipating, like here we're anticipating the carbon footprints, but it could also be anticipating cost and availability in general. And so because an increase in demand for the pulp and paper product or any of the Bloom product will lead to an increase in biomass consumption, and this would create a competition which can be modeled through this marginal mix approach that Matthias took. With the prospective LCA approach, as I said, we were able to anticipate future evolutions in the energy mix, but it is limited because we don't have modification of the technologies for the chemical sector, which is a main contributor of the global warming potential for the pulp and for the Bloom biorefinery. Fourth, for the choice of substituted product, here we don't have any direct drop-in, so we have to test multiple alternatives, and this is, I think, something that could be generalizable to any technology that makes a new product without direct drop-in. Now that we have the substitution approach, we should really investigate how this choice of alternative modifies the LCA results, and that also guides business strategies. And then finally, here we accounted for this biogenic carbon in the biomass, and then we assumed that at the end of life, which we said would be in the year of production, it would be re-emitted. And we don't really know so far how to model the use phase and the end of life of the products because they have not been tested for a long time. But here we conservatively assumed that we would re-emit all the biogenic CO2 within a year. So we might be underestimating this temporary carbon storage, because if a product is used for insulation in the foams that we have in our buildings, we can expect that they would stay in place for 20, 30, even 50 years. And so that really keeps this carbon in place for a significant amount of time. And this we did not model with this approach that we took. So this is something we would want to work further on. So that was it for our presentation. If you want to know more about Bloom and the products that they do, you can scan this QR code. And if you have more questions linked really to the LCA methodology, I think Matthias, that's his email address, would be more than happy to answer to you when he is healthy again. But thank you very much for your attention, and I look forward to the discussion.
Good. Thank you very much, Mary, for this very interesting and detailed presentation. It's great. Just one clarifying question. In the beginning, you were talking about the cradle to grave approach, but in one of your earlier slides, you talked about cradle to gate. Is that a typo or?
Could be. I was also sick when I was making those. So what we had done initially was what I had been doing as part of my PhD. The first LCA that we did, they were indeed cradle to gate. But with the aligned methodology, we wanted to apply this cradle to grave consequential LCA. Yeah, so indeed, here there's a typo. Sorry.
Yeah. No problem. It's just for the
I'll
clarification.
correct it for the slides to be sent. Sorry.
No,
So yeah, it
great,
was
great.
all the results that I presented were really cradle to grave. And as I said at the end, the way we modeled this end of life was just through release of the CO2 at the end of life by incineration.
Okay. Very good. Yeah, and maybe just can you say something about the you as a result? You mentioned that because of the consequential approach, the specific CO2 emissions decreased a bit. Huh? It's somewhere a bit later. Yeah, that's slide number 12, I think.
This one, so this is they are both consequential results. What changed here is the way that the biomass is modeled, because in the first one we assumed that we take we just take the impact factors that come from the eco-invent modeling, which don't ask me how they were actually obtained, but it is consequential still. But what's different with this marginal mix is that Matthias went back into the database and really look at how these impact factors were obtained and made different assumptions in the way biomass is available and how much compared to what. Because as I said, with the example of bagasse, in the attributional LCA, we don't even see that it's used for energy generation, and that if we use this bagasse to make chemicals instead of burning it, then we need more natural gas to fulfill the energy demand. So this is now reflected in the consequential LCA, but with this marginal mix, they were able to modify some of the assumptions that were initially done.
Okay, thank you. Good. Yeah, is there somebody else who has a question or a remark with respect to the very nice work that Marie Jones has done? I'll see a chat message.
If you don't mind reading it, I don't know how to access it.
No, I'll read it up for you. The LCA studies were quite extensive and detailed. Was it easy or hard to find all the required life cycle inventory information? If KCL information was missing, how did you solve the problem?
KCL? I don't know what KCL means, but I'll respond to the other part of the question. Thank you very much for asking about this. And indeed, that's actually what took most of the project, actually generating the results. I think Matthias was very quick at doing it, but it was really this ping pong that we had between Bloom and Aalborg on like which inventory do we use? Because okay, for electricity, like the eco-invent database has a lot of options, but for chemicals that we use in the process, perhaps it's best if I show this slide. We use methyl THF, we use glycolic acid, and those, if you type on the eco query, you won't find anything. So what we had to do also is go one step back and really also look at creating inventories for the chemicals that we were using in the process. And I think as a company, it would be really hard to do that. I did it as part of my PhD project, so looking at it more from an academic point of view. And then it was useful as well for this project and for Bloom in general. But I completely understand your concern of finding good inventories for some of the more niche chemicals that you use in any process. One of the things from an academic point of view, again, that is quite interesting and hyped at the moment is this AI models that are enabled, that if you put the smile, so a chemical representation of the molecule, then it can predict an inventory for you. I know that at ETH Zurich, they have a tool that they use to do that. I don't know how accurate it is for bio-based molecules. I guess not so much because it's really based on historical data, so fossil fuel. But there is hope that with the new technologies that are being developed now, more from a from a methodology development, database curation, there would be more data available. But this is indeed always a limitation of every LCA study.
Okay. Yeah, interesting. This is of course a more general issue. How do I find my data? What strikes me from your answer is that it's not so much the primary data that's the problem for you, but really the secondary data, the data from the databases. And that is something which you have had difficulties. Interesting.